Hey Ramblers, this video covers chapter 1.8 in our textbook and deals with the limit. Now the limit is kind of the most basic underpinning concept in calculus. Really, without our understanding of the limit that we have, we wouldn't have been able to develop the calculus at all. So we're going to start off with a definition of limit, but it's more important that you finish this video kind of with an understanding of what a limit is, more than having the definition memorized. And we're going to bring in some pretty technical terms like deltas and epsilons, and understanding that facet of it isn't quite as important as being able to work with this concept of the limit. Once we've dealt with that, we want to teach you how to manipulate limits. And so we'll teach you what some of the properties of limits are. And then we'll kind of wind up this video by talking about one-sided and two-sided limits. Now, there is a second part of this section that we'll need to cover in the next video, which gets into limits at infinity and other really important ideas, under the limit umbrella, as it were. Okay, so Ramblers, please pause often, take good notes on this section, and thanks for watching.
The concept of the limit is pretty central and important to calculus, but there's no reason to make a meal out of it. I mean, it really is a pretty simple concept. And that is, if you're given some x, let's say x equals c, and c can be any value on the x-axis, then the limit as some given function f of x approaches c, as x is going to c, the limit should equal some value L. So we say the limit is where we expect to find the function f of x as the x value is approaching some place called c on the x-axis. That's a pretty important note to make as you're watching this. And that's really all a limit is. So if that's true, if the limit is where we expect to find f of x as x approaches c, why don't we just call it f of c? Well, let's look at an example of when the limit is not equal to the value. Okay, let's take a look at this example here. Now, if we were asked to find the limit of the sine theta over theta anywhere on this graph, it would be pretty easy to do. We would just, the limit would equal the value of the function. But when theta equals 0, we see that it creates a problem for sine theta over theta, because f of 0 does not exist, because that would create a 0 in the denominator. Nevertheless, the limit as theta approaches 0 of the function sine theta over theta does exist, and that limit is 1. So here's an example when the limit does not equal the value of the function, because the value of the function does not exist there. Now this case is rare. Functions don't normally have holes. Functions don't always have asymptotes. In fact, most of the time when you're trying to find the value of a function, you can simply when you're trying to find the limit of a function, you can simply use what's called substitution. And substitution means that you just plug in c for for x in the function, and that will help you determine what the limit is. So for instance, let's say that I had f of x equals x squared plus 2x plus 3. If you wanted the limit as x approached, say, 4 of this function, all you would have to do is plug in 4 for x. And then you would simply evaluate the function. So you would get 16 plus 8 plus 3, which is 27. And that's the way you'll normally find the limits, is just by substitution. Now we will develop some other techniques that we'll use when some of the problems are a little more troublesome. But let's not get into that now. Let's talk about this definition of a limit then. All right, so if we get a little more formal with our definition of limit, And some would say this is still pretty informal. We would say that a limit is when a function is defined on an interval around c, except perhaps at the point x equals c, like we just saw in that example where the function was not defined at x equals 0. So we would define the limit of the function as x approaches c to be a number L if one exists. Now keep in mind, a limit has to be a number, so the limit can never be infinity. You know, you can say infinity and everyone knows what you mean, but it's actually not precisely a limit. Such that f of x is as close to L as we want whenever x is sufficiently close to c. If L exists, then we write this expression, that the limit of f of x as x approaches c equals L. All right, what are they talking about, this sufficiently close and as close as we want? Let's go and look at the formal definition, and please, you do not have to memorize this, but I want you to have some exposure to this notation and this delta and epsilon business. All right, so this is the formal definition of limit. And it says this: we define the limit as x approaches c to be the number L, if it exists, such that for every epsilon greater than 0, means that we can make it as small as we want, there is some delta greater than 0, which is sufficiently small, such that x, the difference between some x and c, is less than delta, then the function minus the limit is less than e. Wow, that's really, really hard to understand. But what it means is this, that these epsilons are changes in the y value, and these deltas are changes from in the x value from the given point c. And what the limit definition means is, can we get as close as we want to this L by getting smaller and smaller deltas? In other words, can we get inside this 2 epsilon range by making delta smaller and smaller? You can see why I don't want you to memorize this. Really just focus on this idea that a limit is where we expect to find the function as x is approaching c. Okay, let's move on to some other parts of the limit. The next thing we want to talk about are the properties of limits. Okay, these properties are going to allow us to manipulate limits the way that we have other things like logs, and they're just kind of algebraic rules. So let's take them one at a time. The first one says that if b is a constant, then the limit of b times the function equals b times the limit. Well, let's look at that as an example, and it's not so hard to follow. Suppose we took the limit as x approached 2 of 5x squared. Well, we know that just by doing substitution I can plug 2 in for the x squared, and I'll get that 5 times 2 squared, that equals 20. All right, well, what this first rule tells us is that we could pull the 5 out, and so we would have 5 times the limit as x approaches 2 of x squared, which would be 5 times 2 squared, which, guess what, just equals 20. All right, so that's the first rule. Let's take a look at the second one, which may be a little easier to understand, so we may not need to see an example, but it means that if we take a limit of 2 functions added together, then we can break up into 2 individual limits, and that works over addition or subtraction. With number 3, it's the same thing. You can evaluate a limit of a product of 2 functions by taking each individual limit. You don't need to do them together. And not surprisingly, with number 4, you see that you can break up a quotient into 2 individual limits as well, provided the denominator is not approaching 0 as x approaches c. All right, the last 2 are pretty easy, but they're probably the most useful. So if we were to take a look at number 5, and let's put some numbers in. So they're saying that for any constant k, let's say k equals 3. So the limit as x approaches 200 of 3 equals 3. And that should make sense because In this case, the function is just 3. It's like a horizontal line, y equals 3. So of course, the limit is always going to be 3. Let's take a look at number 6. That says the limit as x approaches c of x. Well, this is just going to equal c. Let's plug some numbers in. The limit as x approaches 20 of the function x. Well, simply by substitution, that's going to be 20. All right, these are the properties of limits. We'll probably get some chance to work with them in the exercises. But let's move on to one- and two-sided limits. A very important topic for us in calculus as they relate to limits are one- and two-sided limits. And, you know, like most of this, it's really not as complicated as you may fear. A one-sided limit is where we expect the function to be as we're coming toward a given x value from one side. So for instance, as I look at this example here, as I approach 2 from the negative side, or as we say from the left side, the function appears to be going to some value L1. So even though the function is not defined when x equals 2, the limit as x approaches 2 from the negative side, that's what that negative after the 2 means. Doesn't mean negative 2, but it means toward 2 from the negative side, equals this number L1. Now, as I approach 2 from the other side on the x-axis, the function is going toward a different y value. So the limit as x approaches 2 from the positive side, that's what that little positive sign after the 2 means, the limit as x approaches 2 from the positive side equals L2. So we would say that the two one-sided limits are L1 and L2, but the two-sided limit does not exist. And that is because the two limits are not the same. Now that's very important, has important consequences coming up as we start to talk about the idea of continuity. The two-sided limit only exists when the two limits coming from either side are the same. Let's take a look at that first example just to solidify that. Okay, in this example here, as we approach 0 from the left side, the function is approaching 1. And as we approach 0 from the right side, or the positive side, the function is approaching 1. So we would say that the left-handed limit is equal to 1, that the right-handed limit is equal to 1, so the two-sided limit is equal to 1. Even though the function is not defined at theta equals 0, the limit does exist because the two one-sided limits were the same. Okay, Ramblers, that's a lot of information for one video, so I'm going to wrap it up here. Thanks for watching, and I hope this helped.